Hello everyone, in this video clip, I would like to talk about the interpretation of regression models with logarithm transformation. Taking natural log is one of the most often seen data transformation in the regression. And there can be multiple reasons. For instance, you can have data that is initially, the raw data is too skewed, so you take the logarithm to reduce its skewness. But you can also have some regression models that is based on some underlying macroeconomics models. And the mathematics may require that some variables must take the format of logarithm. So regardless of the reasons, and you often see variables in log in the regression equations. So here I would like to explain why in the interpretation of log models we usually talk about the percent of changes. And also I would like to give you some warnings about what you should watch out when doing the interpretation. Depending on which variables we take the log transformation, then we roughly have these following four kinds of models. So if you do not take a transformation, then we call the variable is in its level. And if you take the log, then it's in log, of course. So you can have the level model where the left-hand side y variable and the right-hand side x variables are all in their original form, in their levels. And you can have the level log model, that is, you take the log on the x, and vice versa, you can have the log level model and the log model. Now let's look at the interpretation. The level model is clearly very straightforward, and assume that b is positive, then we have 1 unit increase in the x variable would lead to b unit increase in the y. And if you ask why this is the case, then just look at the right part of the equation, so it's very straightforward. And if you have the model with logarithm, then the usual way of interpretation is to associate the change with percent. So if you have the log level model here, then we would say if you have 1 unit increase in the x variable, that would lead to 100 times b% increase in the dependent variable y. Or alternatively, if you have 0.01 unit increase in the x, that would lead to b% increase in the y. And then if you look at the level log model, that is, now we take the log in x, we would say if you have 1% increase in the x variable, that would lead to 0.01 times b increase in the y. And for the log model, we say 1% increase in the x leads to b% increase in the y. And now let's look at the three models with logarithm again, and then what you can discover is whenever you take the logarithm transformation on a variable, then in the interpretation it becomes percent. And this is what you see in the textbook examples. Therefore, now the question is why taking logarithm is associated with the change in percent. So to understand the relationship between the log models and the usual way of interpretation in percent, we should realize that this way of usual interpretation is actually an approximation. We can also interpret the log models with the exact changes in between the x and the y variables, just the same as a level model. So let's consider the following log level model where you have the log on the y variable. You can write down the following equation, and that literally means that if you have 1 unit increase in the x variable, it will lead to b unit increase, and it is in the log of y. But most probably what you are interested in is not the change in terms of logarithm, but you are interested in y variable itself. So the next step we are going to take is to convert the change of logarithm into the change of the level of y. So you can write down the following expression, that is the new log of y equals the initial log of y plus b, and then by taking exponential you see that the new level of y equals the initial level of y times the exponential of b. To put it in another word, if you have 1 unit increase in the x, then the increase of y equals exponential of b minus 1 and times 100%. So you see that this is different from the usual way of interpretation, and the expression is clearly more complicated. But here we didn't make any approximation, so this is the exact change of y in relation to 1 unit increase in the x. There's no black magic, no approximation. It's more complicated, but it is always working.
Nice.
But in many cases and in the textbook, we usually talk about just 100 times b% for the log level model. And the reason is very simple, that is, this usual way of interpretation gives you roughly the same results as the exact method if you have a relatively small x. So in mathematics, we have the outcome that the exponential of x minus 1 is roughly equal to x itself when x is small. To understand why mathematically it is true, then we can consider a Taylor expansion around x equal to 0 for the function exponential of x minus 1. I'm not going to explain the Taylor series, but you see this is an expression with the polynomial of x. Namely, it equals, well, x times something plus x squared times something plus x to the power of 3 times something and blah blah blah. But if you have x that is very close to 0, then the higher order terms are only going to be smaller and smaller. So it is safe that we can just ignore the higher order terms and only consider the Taylor series up to the first order. And as a result, what you can see is that the exponential of x minus 1 is roughly equal to x itself. And if you don't trust the mathematicians, no problem, just take out the calculator and calculate exponential of x minus 1 for a small x, then you would find that roughly it gives the x itself. Of course, you can also try with Excel.
Sir, yes, sir!
So we now know that the usual way of interpreting the log model is actually an approximation, but it has the very good advantage being very intuitive. You can always technically use the exact way of interpretation, but it is more complicated. Not necessarily computational complicated, but sometimes you will encounter trouble in explaining to some audience. For instance, you can think of some politicians who are trained in history but have no knowledge in mathematics. But the usual way of interpretation is crucially dependent on the assumption that the change will be small. If it is very different from 0, then actually the higher order terms in the Taylor series will explode in an exponential speed. And then if you still use the usual way of interpretation, it will lead to a large disparity from the truth. And here I will give you an example. So we consider the following wage regression where you have the log of the wage on the left-hand side, and on the right-hand side there is a dummy indicating whether the person is a manager or not. So if you compare the wage differences between a manager and a regular worker, basically you are turning the dummy from 0 to 1, and you see the coefficient here is 3. If you use the usual way of interpretation, ceteris paribus, then a manager earns 3 times 100, that is 300% more than a worker. But actually it is very naive if you compare the manager with that fat cat. Recall that we need the change to be small in order to use the approximation, the usual way of interpretation. There's no consensus on what is the threshold, but typically if it is larger than 0.4, 0.5, then I would be personally alerted. And 3 is definitely a huge change that will make a big difference. So if you take the exact way of interpretation, then turning from a worker into the manager would lead to a 3 increase in the log of the wage. That would give you 1,900% higher wage, or a manager actually earns 20 times compared to a typical worker. So the picture in the firm would be instead this one.
No! God, please, no! No!
And in determining whether it's safe or not to use the usual way of interpretation, our focus should be the total possible change in the log of the value. So we are not only looking at the coefficient itself. So this time we consider the following regression where on the left-hand side you have the log of revenue in the firm, and on the right-hand side we have the same coefficient of 3, but it is in front of the variable SHE, standing for share of high educated workers. And let's assume that in the database SHE is in the range of 0.3 to 0.5. In this case, it does not make sense to talk in the way that SHE would increase by 1 unit. Basically, it's not possible in the database because you don't make a comparison between two firms and one is fully highly educated and another is totally without any high educated person. Instead, it would be more reasonable if we look at the incremental of high-skilled share by 0.1 or by 0.01, namely 1 percentage point. So 0.03 is actually a small number, so it is safe to interpret in the usual way, that is, for every 1 percentage point increase in the share of high-skilled worker, the revenue of the firm would roughly increase by 3%. So to give another example, we can also have a different scenario in which the coefficient itself is small, but the total change in the log of the value is large, such that we have to use the exact way of interpretation. Let's consider the following example of uncontrolled reproduction of rabbits. So for simplicity, we assume that a couple of rabbits, that is one male and one female rabbit, they will give birth to 4 rabbits every half year. Namely, the new generation of the rabbit population will double for every 6 months. And if we take months as the unit of measurement of time, then we can write down the following expression, and it roughly gives you that the coefficient in front of time would be 0.1155. And you can verify that if you use the exact expression for interpretation, then plug in the time equal to 6, then you get doubling in the rabbits. So given the relationship in this equation, the coefficient of 0.1155 is very good to make short-run predictions. That is, if you consider the time going on, then every month the population of rabbits would increase by about 12%. But it would be problematic if you take the coefficient and use it in the usual way to directly make a prediction for the long run. So now let me ask this question. Assume you believe this equation and you have 1 rabbit to start with. How many rabbits would you get after 10 years? So sorry, this is actually a code joke, so if you have 1 rabbit to start with, then after 10 years you get a dead rabbit, sorry. So let's consider something more serious and give it a male rabbit, so they can start to have the reproduction of new generations. If we use the usual way of interpretation, then 10 years is 120 months. So you use 120 times the coefficient, which is roughly 12%, and it would roughly give you the increase of rabbits by 1,440%. That is, the rabbits after 10 years would be about 15 times than the initial population. However, if you calculate the exact expression and plug in t equals 120, then you would get 1 million times more of the rabbits. So here the usual way of interpretation is seriously underestimating the rabbits, and the true value from the exact method is totally different from the approximation. So I hope that you have learned something about how to interpret the model with logarithm, and in particular when you should bring in the exact method of interpretation. And in the very end, I would like to still say something, that is about, say, if you know some trouble is going to develop at an exponential speed, no matter how small the speed looks like, and if you give it enough time to evolve, then the small trouble will eventually develop into something that is totally uncontrollable. For the rabbits, it is what has happened in Australia 100 years ago, but perhaps now we are facing with some new challenges. So take care, and I hope everyone stays safe and healthy.